Well, hello and welcome, YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based, of course. And as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on aside, and we are going to be dealing with reviewing everything that we've been doing on graphing. I don't know how much I've done in video form in this unit of stuff so far, but they're radicals. Graphing radicals, simplifying radical expressions, and solving radical equations. Now, I just came off a video where I was doing something for another class where we were simplifying radical expressions, and I'll tell you what, unless something changed, and I don't think it did, I pulled 9 problems from the 24 problems that you're going to see on here with it. So what I'm going to do, at least for my class, if they're listening here, is I'm going to skip past, when it comes to me recording right now, I'm going to skip past me doing those 9 problems where I'm simplifying the radicals in this recording. What I'm going to do is edit this recording so that I put in the problems that I did from the other video. So this video will be edited and sequenced as if maybe there's no real jump. I just came off that recording. The only thing that there may be that's a little weird is I don't know if I didn't start talking about something, like, maybe you're coming into something out of context from what I explained from a previous problem and you're just hearing it for the first time. That's the only part I'm uncertain about. I couldn't tell you. I'm not listening to that part of that recording right now. But I think it just makes more sense. I shouldn't re-explain something that I just had a recording for. That's the point of these video guys. It's not just to have for this year. It's to have for future years always, and future proof as long as we do problems like this in the future. Clearly tends not to be the case, because this is like 15 years I've been doing this kind of stuff, and I seem to always keep making new videos. That being said, I'm going to dive straight into the action. We're going to do some graphing here. So let's go ahead and look at this front page together. We're going to graph the radical equations below. Consider transforming any into graphing form that are not beforehand, that were not in graphing form beforehand, I should say. So what we're doing for a graphing form here, guys, is we're taking some sort of function, and we have an a stretch factor, and this will be multiplied by the square root of, and there's going to be some sort of x minus h and plus k. Now, some things to keep in mind here. Number one, the a, h, and k are what they always have been in previous things. A is a vertical stretch factor, and h and k is your reference point. In some cases, for like a square root, it'll be your vertex. You got hk. And when we do a cube root, it'll be that center point. Next thing is this. It is possible that the quantified thing in front here could, besides have a positive here, it could also be a negative. And if it's a negative, that's an indicator that your graph is going to the left. I'll show you what that looks like when we talk about like domain of our graph here, because our first graph does this. F of x equals 2 times negative the quantity x minus 1 minus 2. Now, I don't want to do anything with this negative. First of all, I can't pull it outside of here. It's inside of a square root. The square root's protecting it. Second of all, I'm not taking square roots of negatives. In fact, it's about finding the x values that don't give you negatives into here. And that's kind of what I want to start with, just talking about and getting you an understanding of why this graph goes left. What I'm going to do is look at this domain and state that whatever's inside the square root function, this negative x minus 1 quantity, this whole thing has to be 0 or positive. It cannot be a negative number, ultimately. So as far as solving for what x can be within here, you got a couple things. You could distribute this negative into here, and you get negative x plus 1 is greater than or equal to 0. If you subtract 1 from both sides, you get negative x is greater than or equal to negative 1. And then if you divide both sides by negative 1, you get positive x here, 1 here, and dividing by a negative means the inequality symbol flips. We get less than or equal to. And this is the domain of this thing here. The domain meaning the x values that I'm able to substitute into this graph and get real numbers out, get an actual y value for. And what this thing is telling you right here is from 1, and not that this is part of the graph, but from 1, the graph goes to the left. From here, only points to the left of 1 count, including 1 itself. So this graph does not go to the right, it goes to the left. Now, if you haven't done any square root things with me before, square roots are basically sideways parabolas, only it's half of a parabola. So instead of something going like this, it's more going like, in this case, to the left, but only half of it is happening because of the idea of functions. You can't have multiple y's for the same x value. But a lot of things are going to apply the same way that we have in the past, such as we have a vertex at the point hk. My h is 1 because we flipped that sign. My k is negative 2 because we keep that sign. So I'm going to start at 1, negative 2 right here. Now every point hereafter is going to be take on that square root behavior for y. As I displace myself to the left, 1, 2, 3, 4, 5, 6, 7, 8, I'm going to go up the square root amounts of those values. Not only that, but then I got to double that value because that's what a vertical stretch factor is going to do. So normally when I would go over 1, I would go up the square root of 1, and the square root of 1 is 1. But I'm going to double that height now. So when I go over 1, I'm going to go up 2. Now, I'm not going to try and do something with going over 2. When I go over 2, I would be going up the square root of 2 and then double that. The square root of 2 is not a perfect square. I don't want to take the square root of 2. I don't have to. You can't make me. Square root of 3 is the same kind of issue there. Square root of 4 is fine, though, right? 1, 2, 3, 4. I can take the square root of 4 and I get 2. That's how much I'm going to go up if it weren't doubled, but we are doubling it. So you double 2, you get 4. What's the next perfect square on our ledger? Not 5, not 6, not 7, not 8, but 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. The square root of 9 is 3, and I'm going to double 3, and I get 6. Again, the doubling comes from the vertical stretch factor right there. I can fit one more here, and that's if you go over 16. I think 16 is this far over right here, and the square root of 16 is 4. So 1, 2, 3, 4. Let's double that, 5, 6, 7, 8, and we get this point right here. So some beautiful points there when it comes to graphing this function right here. And this will be a leftward facing half parabola like this. There we go, much better. Oh, that's okay. I'm going to keep it. No, I'm not. It's pretty good. Okay, except for the front. All right, so there's that first graph right there. And that domain really took care of the idea of the negative, this and that, what's house. Now, a cube root right here. If we were going to deal with a cube root, and I'm not going to be up here anymore for this part, cube root's there. Everything's the same, only we don't call this a vertex, we call it a center. And there are no domain restrictions because we can take cube roots of negatives. Furthermore, the cube root won't have a negative on the inside anymore. If there ever is a negative inside that cube root, we can take the cube root of a negative and it'll become negative on the outside. Having a negative on the inside versus a negative on the outside, those are identical for cube roots. Square roots are way different stories for it. So we have f of x equals the cube root of x plus 3 and then plus 4. So the center of this thing here is at negative 3 comma 4. Flip this sign, keep this sign right here. So we're going to start at negative 3, 4. And now the cube root fashion states that just like square roots of before, however far we go away in the x directions, we will go up or down, a certain y amount by taking the cube roots of those numbers. So I can take the cube root of 1. If I go over 1, I can go up the cube root of 1, which is 1. Now the cube root of 2, that is not a value that we're going to be playing with. I don't know the cube root of 2. You don't know the cube root of 2. Or 3. Or 4. There's a square root of 4, but there's no cube root of 4 that's a perfect cube. What's the next perfect cube value? It's actually 8. 8 is a perfect cube because the cube root of 8 is 2. So I can go 8 over, and I can go up 2. If you notice, guys, there is no vertical stretch factor change. It's just a positive 1. Nothing's really happening there. So I'm just going up the amount that I'm cubing and cube rooting. The next one over would be 27 because that's 3 cubed. I cannot fit 27 on this. It's way too far. It's about 7 units out of reach there. It would be somewhere kind of right off the edge of the screen, like right over there. But I don't actually know. But here's the thing. These are not half parabolas. You can take cube roots of negatives. So if I go one to the left, that's going to be the negative portion of the cube root. And the cube root of negative 1, the cube root of negative 1 is negative 1. So I'm going to go down 1 like that. And the cube root of negative 8, I think right here, is negative 2. So you can see what's happening with this kind of split thing as it stretches off into the unknown. Right here. Oh, that's way too far. I'm not going to bother with that. But I am going to bother with this, where it hits through this point, and this point, curves into it, curves out of it. You can't make me. It's harder with my touchpad. I apologize. But there's my graph. Close enough. There's my cube root. Okay, one more square root, one more cube root to graph. Now, these two need some manipulation to get into that form that we're talking about. Like, I want an a value. I want a stretch factor. And I don't want anything inside of this square root that's not some h and some x, a 1x, mind you. Maybe a positive, maybe that minus there if I absolutely had to. And there's no choice if it's there. But right here, I have this 9. And it has no business being here. Furthermore, that's 72. That's not your x value of your vertex here. You have to begin by factoring that 9 out of both of these terms here to get x plus 8. Because what we have to do is exercise a property, which, by the way, is a part of our exponential property things, that if you have a square root of a product, that can be broken up into the product of two square roots like this. So when I split this thing up here, I'm going to have the square root of 9 times the square root of x plus 8. This may look weird to you, but I'm not finished with this thing. 9 is a perfect square, and I can take its square root. Just for room's sake, I'm going to go and erase this. The square root of 9 is 3. So this function ends up actually looking like this. 3 times the square root of x plus 8. Oh, not plus 6. I'm sorry, that's a minus 6. 3 times the square root of x plus 8 minus 6. Like that. So this is now that graphing form where you have a times the square root of x minus h plus k. Now the x minus h is a plus 8. That's a negative 8. 1, 2, 3, 4, 5, 6, 7, 8. And then negative 6 is the vertex right there. And from here, we're going to plot all of our other points. Square root graphs should naturally go right unless we were doing something with a negative inside of the square root. And it'll also go up because the stretch factor is positive 3. When you go over 1, you go up the square root of 1, which is 1. And we are going to triple that value and get 3. When you go over 4, 2, 3, 4, you're going to go up the square root of 4, which is 2. Tripled is 4, 6. When you go over 9, you can go up the square root of 9, which is 3. Tripled is 6, 9. When you go over 16, 10, 11, you can go up the square root of 16, which is 4, tripled, which is right there. I don't know if another one can fit here. It would be, how far away? 25 away from that can't, I don't think that can fit. So I'm going to be done with that right there. Let's draw this very beautiful one. So you can tell how much you're going up, guys, right? We went up 3, and then 6, and then 9, and then 12. How it kind of just builds off that. And there's that half. Remember, it's half a parabola. Here's that other half the parabola we're not really drawing because it's not a part of it. Last one for cube roots here is the same kind of idea as before. We need a transformation within this guy right here. And within this transformation, I have a cube root of 8 times x. The cube root of a times b is the cube root of a times the cube root of b. So I am going to take that cube root of 8. I'm just going to go ahead and write what that part is right there. So f of x equals, I got negative 2 times the cube root of 8 times the cube root of x plus 1. This thing really had a beef with that 8 right there. We can take the cube root of 8. We get 2. So negative 2 times the cube root of x plus 1, which is negative 4 times the cube root of x plus 1. So here's another graph to do based on that information there. Now, this one seems to be missing the h value. The h value is a way of having horizontal translation. So if it's missing, it must mean it's 0. So we are not going left to right at all on this graph. The graph is going to go left to right. But the initial spotting of the graph, the center for this thing is going to be at 0, comma, and then this is a 1 right here. So 0, comma, 1 like this. And that's where we're going to start this thing. Now the negative 4 states that this graph will be flipped over. Instead of going this way, right and up, we're going to be going right and down. This graph is going to have something along the lines here. Now, we still have to do those cube roots. When you go over 1, I'll just say down. You're going to go down the cube root of 1, and you're going to quadruple that. 2, 3, 4. when you go over 8, right? 8 is the next cube root. You're going to go down. Cube root of 8 is 2. Quadrupled. Sorry, cube root of 8 is 2. Quadrupled is 2, 4, 6, 8. Right there. And I probably won't fit the 27, so I'm going to go on the other side. 1, 4. And 8. I guess 8. Like that. Let's see how I can make this cube root look, because it's my last, I think, graph drawing. Pretty good, huh? Actually, I like that one. All right. Good. Okay, guys. I got 2 more things. This time we're writing equations. Now, I didn't do these in particular with my students before, but that's not to say that we can't now that we understand what's kind of happening. Write the equation for the following functions in graphing form, which means you have to consider your whole a, h, and k stuff. So again, the formula for this thing, whether it's a square root or cube root or whatever, it's a times that root of some x minus h plus k. There can be a plus or minus thing involved. Obviously, if it's a plus, you don't write anything besides the x minus h. But I'm looking for a stretch factor with these, and I'm looking for the vertex or the center with these. So with this first one right here, we got a vertex at -4, 0. That means your h is -4. Your k is 0. So when it comes to an equation for this part, now I haven't gotten a yet, and this graph goes to the right, by the way. It goes down, but it goes to the right. So it's x minus h plus k. So the plus 0 means that 0 is actually also kind of just gone. We're not done, though, yet. We need to figure out a, that stretch factor. Figure out the displacement. We're going 1, 1, 4, 2, 9, 3. That looks familiar. 16, 4. Okay, that's good, but it's going downward. That means you have a negative stretch factor. This is a -1. Nothing else really changes to it, and that is your equation for this graph. That's how you would draw the graph based on what that looks like. And then we have number 6 right here. Oops. By the way, that was a square root, right? So number 6 here in this case looks like a cube root graph. So you already know part of the nature is this will be a cube root here. Now your center is at 1, -1. So that'll be some form of that x minus 1. Excuse me, 1, 1, not 1, -1. 1, 1. So you do x minus 1 here and then plus 1. You got to figure out the stretch factor. When it goes over 1, it goes up the cube root of 1 tripled. When it goes over 8, it goes up the cube root of 8 tripled. It looks like we are tripling our values there, not multiplying by a negative because this goes right side up and all that jazz. And that is the final result to that one. Okay, it is at this point, guys, I'm going to flash it to you, but it is at this point that I'm going to be dealing with some problems here. Let me see. I just did these problems. Let me see if they look identical. They might not be the same number that you'll end up seeing from the previous thing. In fact, they're not. So what you're going to do is I will edit this in the way that you will find these problems. They'll have a different number on them, but the problems should be the same. So these are the other 9 that are going to come into this video right now. Now we're going to be dealing with rational exponents and keeping in mind the general property. I think I got to write it for you guys. That this converts to this form right here, radical form. And the first 6 problems, I'm not actually going to use variables. We're just going to evaluate these numbers the way that they are kind of deemed to go. That doesn't mean other exponents, or other properties don't fly in the way, such as the negative exponent. We've seen several problems that negative exponents in succession, and this doesn't stop right here. So let's deal with that first. Negative exponent turns positive if I flip the quantity, 25/9 raised to the 1/2 power. Now I can take that 1/2 power and I'm going to go ahead and do 25 to the 1/2 power and 9 to the 1/2 power, unless you want to convert it into its radical form right now. It's kind of your call here. If you want the radical form of this, keep in mind, guys, if I had some sort of, what will I do right here? Let's do that first. The x to the m over n equals the nth root of x to the m power. So the 2 down here represents the root for which we are going to be applying this radical. And 25/9, see, this is why I don't like to do this here. 25/9 is all raised to the 1st power, which really is just a fancy way of saying the square root, right? We don't write it 2 when it's square root. The square root of 25/9. That's what we're doing here. And in order to do this, there's another property that we have there that says when you take a radical of a product or of a quotient, you take the radical of both parts, top and bottom. Square root of 25 over square root of 9. And I wanted to convert them radical form because we know how to use these. We know how to do them here. 5 over 3. Now what you could have done alternatively was taken the 1/2 right here, and you would have gotten 25 to the 1/2 power over 9 to the 1/2 power. And guess what? It brings you right back to here. 25 to the 1/2 is square root of 25. 9 to the 1/2 is the square root of 9. And then we're kind of done on that. Number 14. More of the same, only this the rational exponent is now positive, so there's nothing to flip. We'll leave them as they are. And, I can go straight up into this one. I'll kind of do that opposite approach that I did last time. 16 to the 3/2 power divided by 81 to the 3/2 power. Now, this doesn't mean you take 3/2 of 16, right? It doesn't equal 24. What you're going to do, though, is you're going to take the square root, that 2 would go here if we ever wrote it, of 16 cubed. But I'm going to cube last. I want to take the square root first. I don't know 16 cubed off the top of my head. I know the square root of 16 off the top of my head, and I might know that number cubed off the top of my head. Now here we get to take the square root of 81, and we also cube that value. Now the square root of 16 is 4. Let's cube that. And the square root of 81 is 9. Let's cube that. Not terribly small numbers here. The 4 cubed is 64. 9 cubed is 729. I just got a loud, annoying buzz in my ear, like a ringing. Like, my mom always complains to me about her tinnitus stuff now, and she says this buzzing in my ear won't stop. If I heard this all the time, I would go crazy. I hope this stops very, very soon. She always also tells me to not watch movies so loud, because I do that in my house all the time. Big home theater thing that I just do in my house. Hope this goes away soon. 121, I feel like I'm talking over it now. 121 to the 1/2 power. That converts to, once again, that's the square root of 121. The square root of 121 to the first power. Plus 125 to the 1/3 power, that's where you get the cube root of 125 to the first power there. The square root of 121 is 11. The cube root, I think it's going away. The cube root of 125 is 5. 11 plus 5 is 16. 19. This is where we start dealing with things with radicals and rational exponents and things like that. Okay, so I don't know if it's going to show up. I think it does maybe in the last problem. But our final answer can only have positive integer exponents. That means only radicals ultimately in the end. That doesn't mean that right now I'm going to take x to the 1/2 power and turn it into the square root of x. No, in fact, as much as I loved using radicals for these guys right here, square roots, cube roots, and stuff like that, you really probably want to think of these in these forms here for several reasons. The main one is we can't take a square root of, if I ask you what's the square root of 9, you can say 3. If I ask you what's the square root of x, there's no answer to that because we don't know what x is. It's just whatever the square root of x is. So what we want to do instead is work with how the root version or its rational exponential portion can interact with other exponents in the properties that we're going to be playing with here together. So what I can do is take this x to the 1/2, and I can, I'm going to take this 4, and we are going to, apply it to the x to the 1/2 and to the y to the 1/4 right there. So we have x, I'm going to write this one out so you can see it in full. X to the 1/2 to the 4th times y to the 1/4 to the 4th. Now over here, we could do that equivalent. At least I can give you the written version of that. Keep in mind, when you take the cube root of this here, you're taking the cube root of kind of both of them, right? In fact, let me write the in-between step there. I'm going to put a few steps on this one since this is the first of its kind. You get to take the cube root of both of these as well, y cubed like that. Now, with this one, and I know that you know what's going on, but because it's a fraction, I want this to be a first-time thing. We're doing 1/2 times 4. Which also means 4 divided by 2, as we'll get to that. And then this is y to the 1/4 times 4, which of course is 4 divided by 4. Now with these ones, if you prefer to rewrite them in their rational exponential counterpart right here, this will be x to the 6/3 power. See, now you know how these things work together here. And then y to the 3/3 power, like that. Now, you don't have to write it like this. What you do have to know is that these divide, 6 divided by 3. and 3 divided by 3. So I will often go without writing this version of this unless it's already provided that way, and it's going to interact with other things such as powers. Otherwise, I'll note that that 3 is the division for this thing right here. Now, 1/2 times 4 is 2, so that's x squared. 1/4 times 4 is 1, so you get y. And over here, 6 divided by 3 is 2, so that's x squared. And 3 divided by 3 is 1, so you get y. So we got x squared y times x squared y, or really x squared times y times x squared times y, which does become x to the 4th times y squared. Okay, number 20. We can probably, at some point, these don't necessarily get harder. There's some parts that you have to rewrite, but we got the radicals involved. Let's live off what we just did on the previous problem to kind of make sense of how you can do a lot of these in very few steps. You have y to the 1/3 power all raised to the 6th. That means these two will multiply right here. 1/3 times 6 is 1/3 of 6. 6 divided by 3 is 2. So the top ends up just being y squared. On the bottom, I just made mention of this with like the 6 and the 3, and the 3 and the 3. That 15 will be dividing by that 5. You don't necessarily have to write that portion if you understand what 15 divided by 5 is, which is 3. Now we could be done, but we're not because we have a y dividing by another y, which means they can intermingle right here. I can remove all two y's on top and be left with 1. Remember, there is a 1. And on bottom, I'll remove 2 y's from the 3, and I just have 1 y down there. So this is going to become 1 divided by y, ultimately. That is the final reduction simplification of that one. Number 21, we have x to the 18th to the 1/3 power, and of course we will multiply the 18 with the 1/3, or 18 divided by 3, and we get 6, okay? And then we have the square root of x to the -8th power. Now remember, square root, if you don't see what's written, we're seeing squared, right? 2. You're going to be doing -8 divided by 2, and that's -4, so that becomes x to the -4th power. Now you may either add these immediately right here, or you can put it, say, in fraction form, x to the 6th over x to the 4th, as that goes down to become a positive exponent. And now we can do what I generally do, is remove all 4 on bottom, remove 4 from the top, and you're left with 2. Your ultimate simplification is x squared. Okay, I have 3 more problems for us to do. See if we can end maybe by the 15-minute mark. Maybe, maybe not. Number 22, we just did the square root of x to the -8th on the previous problem. Now we have x square root of x to the -10th here. You are dividing -10 by the invisible 2 that was, and that becomes x to the -5th power up top. On bottom, by the way, you can't do things with these yet, because this has a square root, this has a squared quantity. X to the -3rd is going to get squared here, and that results in -3 times 2, multiplying right there, and that's x to the -6th. So not done with this thing here. I'm going to take this guy and move it down, and I'm going to take this guy and move it up as I change their signs, and I'm going to get x to the 6th over x to the 5th. And of course, we can then divide these things here. Remove all 5 x's from the bottom, remove 5 from the top, and you're left with just 1 x right there, or as I can just say, x. You could use your division property here. That would be x to the -5 minus -6 power. Probably a lot of negatives for someone to work with, but you will get x to the 1st power from that. It's not like you won't. Okay, number 23. Again, multiple ways to look at it. Let's look at those multiple ways. One way is to maybe just work from the inside right here, and you can take 8 to these powers, which means, or to the whole thing, which means you're multiplying 8 by 2 and 8 by 4, and you'd get the 4th root of x to the 16th times y to the 32nd power. Then that 4th root says we're going to take each of these exponents right there and divide them by 4, right? So you'll end up getting x to the 4th times y to the 8th. So that ends up being the final answer, and that's one way of going about it. Alternatively, maybe you could have just worked with the 8 and the 4 to begin with. If you recall, this is a quantity right here. So the root of a quantity raised to a power is also equal to that quantity raised to the power divided by the root, 8 divided by 4, like that, which is, of course, 2. So you could have one version where you have x squared y to the 4th squared, And then you take that 2, of course, and you square the x squared, which is x to the 4th, and square the y to the 4th, which is y to the 8th. And lastly, number 24 here, we do have the square root of 1,000 times x to the 15th times y to the 20th. This time I'm going to separate them because I got to really focus on the numbers before I get any of the variable things. And this time we have something slightly different with the x variable. I'll show you what it is. Let's start with the square root of 1,000. Now it's not a perfect square. It's not just a single number and boom. It is, the largest perfect square I can pull out is 100, and there's still a 10. The square root of 100 is 10, so I have 10 root 10 from the square root of 1,000. Now, x is a different story because, as we talked about for exponents, of course, we divide by the root that's out here, in which case is 2. Y to the 20th, square root of y to the 20th is 20 divided by 2, which is y to the 10th. That one's fine. But x has a 15 divided by 2. And no, we're not going to start writing decimals like 7.5, 7.5, whatever. We are going to divide out as much as we can. And, we did this over here as well with the 1,000. We factored out a perfect square of 100, which is 10 squared, and took its square root because you can take its square root. We want to find something that we can take the square root of inside x to the 15th. And the largest value you can is not x to the 9th, but x to the 14th. Because remember, you're not taking the square root of 14. You're dividing 14 by 2. Now, x to the 15th is x to the 14th times x. So I'm going to split this up into two things here, of which I can or know how to take their square roots. So the square root of x to the 14th is 14 divided by 2, there is 7. So you get x to the 7th. That root x stays inside the radical, just like this 10 did. We can't take its square root, so we won't try. And we have y to the 10th there. So ultimately, what you want to do, another simplification property is kind of just one radical, especially if they are the same root. So I have 10 x to the 7th times y to the 10th times the square root of 10x. Little more confusing looking in the final answer, but that's kind of what's going on there. Okay, the last problems we're going to do here are solving radical equations. And honestly, I think these are probably easier than simplifying the radical expressions and all that kind of stuff. We got to check for extraneous solutions, which I'm not going to get deep into other than we try and plug in our answers back into radical equations, and there's a reason why you might run into extraneous solutions. So in solving radical equations, it's a straightforward process. Your process begins with make sure you isolate the radical quantity. By isolate means have it on its own side of the equation, like this one does right here. You need to do that in order to properly cancel the radical. We're not going to do anything inside the radical except for try and come up with squaring it to get rid of it. So the first thing I'm going to do is square both sides of this equation, because when you square a square root, you're just left with the inside radicand value, which is this. Now, x plus 5 quantity squared. I haven't done one of these with you guys for a while, but that is a perfect square trinomial, where you square the first term, you double the product of your two terms, and you square the last term. It is not x squared plus 25. It's x squared plus 10x plus 25. And now we've created a quadratic for which we're trying to solve, and we've run into a bunch of these on my channel here. Subtract 3x from both sides, I get 7x. Subtract 13 from both sides, I get 12. And you set it equal to 0. Assuming it's factorable, which it is, you then try and find out what those values for x can be. X plus 4 times x plus 3 equals 0. If x plus 4 equals 0, then x equals negative 4. And if x plus 3 equals 0, then x equals negative 3. And these would, ideally, be our two answers here. Now, there's a chance of extraneous solutions, which means trying to substitute these solutions back into the original, the OG, the original equation right there, and then seeing if you actually get a true statement. Normally, what would happen if they're extraneous is normally they would end up being on, you get like a positive negative version of an answer. It might say 4 equals negative 4 or something like that, and of course, that's not true. But so here's what we're going to do. We're going to try and plug in negative 4 into here. Let's do it mentally and see what we get out of that. So we'll get 3 times negative 4, which is negative 12, plus 3, which is 1. So I got square root of 1. I guess I can't do it fully mentally. Square root of 1. And then x plus 5, negative 4 plus 5 is 1. The square root of 1 equals 1. 1 equals 1. That checks out. It looks like negative 4 works. Now I'm going to go to negative 3. So we substitute negative 3 into here. We get negative 9. I'll say negative 39 because of the 13. Negative 9 plus 3 is the square root of 4. There's the square root of 4. And negative 3 plus 5 is 2. Square root of 4 equals 2, or 2 equals 2. That one also seems to check out. Neither of these are extraneous. Both of them worked. Those are your solutions. All right, number 17, we're going to do the same kind of thing here, only you have to make sure your thing's isolated. I can't square right here, guys. I can't just take this thing and square it and say, oh, you square this and that. Unlike your properties where you have a product where you can square such things like this, you cannot do that for a sum or difference. Once this is isolated, you can truly get what you want out of it, not create a perfect square trinomial where you would actually, unfortunately, still have a radical. So what I'm going to do is I'm going to add 3 to both sides right here, and I get x plus 3 equals, and I got the square root of negative 3x minus 11. And now that I've isolated this radical, I can now square both sides here, squared and squared. X plus 3 quantity squared is x squared, square the first term, plus double the product of the two terms here. 3x times 2 is 6x, plus, and then 3 squared is 9. And that equals, so when you square this square root thing, don't change any of these negatives positives. You're not going to do anything like that. You just take the inside quantity, and you are going to then you're going to square the square root portion right here, and then you end up just getting the negative 3x minus 11 bit, just like that. So then what we ultimately do there is we got to, once again, set it equal to 0. Set it equal to 0 by adding the 3x to both sides like this, and add the 11 to both sides like this. We get x squared plus 9x plus 20 equals 0. Okay, so now that we have x squared plus 9x plus 20 equals 0, now we can solve this thing by factoring. We can find out what two numbers multiply, and I don't know if you knew what I did from factoring here. We've done so much factoring here, I just assume that you know. We're finding two numbers that multiply to the product, and two numbers that add to the sum. So like 4 times 3 is 12, 4 plus 3 is 7. Kind of like that. So right here, what times what is 20? 20 that they can also add to 9. 5 and 4. 5 times 4 is 20. 5 plus 4 is 9. So you end up getting that. Zero product property states if this times this equals 0, either x plus 5 equals 0, so x equals negative 5, or x plus 4 equals 0, so x equals negative 4. Now you want to check for extraneous solutions again, because there's a chance it happens with the quadratics for a lot of different reasons. What you have to do is substitute it into any expression or any equation that you have that is not one that happened after you squared it. I tend to want to just plug it into the beginning one. So let's check this thing out. I'm going to rewrite this thing. Actually, let's do a copy paste right here. Copy and paste. Okay, so I have this guy right here. So let's go ahead and try and substitute negative 5 into there. Negative 5 for x equals the square root of negative 3 times negative 5 minus 11, and then minus 3. We get negative 5, and I can give you a reason why I think that this would already be a certain answer that is, but that's okay. Negative 5 equals square root of, that's 15 minus 11 minus 3. Or negative 5 equals square root of 4 minus 3. Negative 5 equals 2 minus 3. Negative 5 equals negative 1. Not a true statement. Not a true statement. If you had the radical isolated, you could work off the isolated radical version right there. I probably prefer doing that one before it's squared, of course. But that's okay. All right, negative 4. Oh, so negative 5 did not work. You substitute negative 5 in here. It didn't work. That's called an extraneous solution. Now, let's hope negative 4 works. Let's just, let's try it, see if it does. So negative 4 equals square root of negative 3 times negative 4 minus 11 minus 3. Let's do a few less steps here. Negative 3 times 4 is 12. Negative 3 times negative 4 is 12. Minus 11 is 1. The square root of 1 is 1. We get 1 minus 3, and it gets negative 4 equals negative 2. Also not a true statement. This is also an extraneous solution. Well, what happens when all the solutions that you find are extraneous? That means we have no solution to that thing. We tried. When we created quadratics out of these things, it created solutions that otherwise didn't exist in the original problem. So we get no solution. Oftentimes you might get one that's extraneous or something like that. It's not often you get none, especially when you solved for things before it. Okay. So these ones here, hopefully you already saw the video for. All right, so that's it for these problems here, where we had the graphing ones to start with here, and then we did the rational. We did them through an edit of the video for these problems here. I hope you're comfortable with that. I hope that they panned out okay, and then you solve these two equations here, or what you could solve. All right, that ought to do it for this one, guys. This is Mr. Robinson. Thank you so much for watching. I hope that this made a good bit of sense here. Take care. See you in the next one.